Okay, I want to go through another example here that is what we typically do when we were running a test in the lab. And with this particular problem, we are going to run a direct shear test in the manner that we've said, where we apply this load P, keep it constant, then we apply F increasingly until we get failure, so that we plot up delta, which is the deformation here, which is the amount that it slides across, versus F. So as we increase F, we get an increase in delta. So we keep increasing it, and what happens is eventually we increase it, and then no matter what we do, it slides, so we can't increase F anymore, but the thing keeps sliding, and then we get our failure. So that is the way the test is run. And in this particular example, we have sand. So we have sand there, which means that when it's sand, for this particular test, the speed of the test doesn't really make any difference, because sand is going to be, unless I loaded it so quickly that it would simulate an earthquake, which we're not going to do. So we're not going to load it that rapidly. So within normal bounds, we will get the same result. So in other words, if we run this test and it takes a few minutes to run it, whether it takes us a few minutes or a few hours, we're going to get the same result. So that is a drained test, because as we said before, that sand and gravel we are going to regard as being drained, meaning the excess pore pressure doesn't build up. Okay, so our goal is going to be to find phi prime. So this is the result of our test. We apply P, we choose that as 30 kilonewtons, and then we increase F, and we found that when F got to be 23 kilonewtons, that we got our peak here, and that was our failure. Our cross-sectional area is 1 square meter. It's a little bit not realistic, but it keeps the math simple, which is what I want to do. And so here's the solution to our problem to find phi prime. Well, it's quite simple. I find tau FF, which is F over A. I find sigma prime FF, which is P over A. And so I get 23 kilopascals for tau FF. I get 30 kilopascals for sigma prime FF. And I plot it on our Moore axes, which are the x-axis is sigma prime and the y-axis is tau. So the x value is 30, the y value is 23. I make a little triangle here that is 23. This is 30. So for that triangle, I can get the phi prime, just noting that the tangent of phi prime is 23 over 30. And that means that phi prime is equal to 37.5. So very straightforward. Okay, so I want you to do this one. Here we choose a load of 20,000 pounds for our P. Again, it's sand. Just do it exactly the same way as I just did. Our cross-sectional area now is 0.08 square feet, so the math is slightly more difficult. This is our stress-strain curve, and it fails at 850 pounds. And so your job is to calculate this and to get phi prime. Okay, so pause the video and do this problem. Okay, assuming that you did it. I just described it, so what do we get? A tau FF is what? 850 over 0.08. Our sigma prime FF is what? 2000 over 0.08. Easy enough. Now this is my X value, that's my Y value. I create this little triangle here, and this is 25,000. So my tangent of phi prime is 10,625 over 25,000. I get 0.425 is the tangent of my angle. That means that my angle is 23 degrees. So that's my friction angle. My phi prime, my coefficient of internal friction, also known as friction angle. It's a number of different names. Phi prime, friction angle, coefficient of internal friction, all the same. Okay, or sorry, angle of internal friction, not coefficient of internal friction, angle of internal friction. All right, so just a couple things that you need to note is that for sand and gravel, the line, which is the failure envelope, we call it the failure envelope, it goes through the origin. For clay and silt, it does not. Okay, for sand and gravel, our failure envelope goes through the origin. As we can see here, it goes like that, from the origin to our point. Now, okay, so I'm going to note, though, that when we have a clay, for instance, clay or silt, and we want the drain strength, then in the lab, our loading is very slow. So we may want to take a few hours to run the test, not a couple minutes. And the purpose of it is, if we load it so slowly, is that we can get the excess pore pressure to be zero during the loading. And we talked about what causes the excess pore pressure is that shear on the shear plane, for instance. And we want that to remain very small. Now, we also note something else that's different for clay and silt. So for clay and silt, we are going to find that we have two phases for the test. So the test is a little bit different when we have clay and silt. We break it into two phases. We have what we call the consolidation phase. Well, what is that? We apply P, our vertical load. And what we do is we let time pass until UXS due to the vertical load has dissipated. We're all familiar with our consolidation test. If you remember that we ran it last semester, or we showed you how to run it last semester, what we did was we applied the load and we let that load, the vertical load, which caused an excess pore pressure due to the vertical load. So remember, we've looked at two ways to generate excess pore pressure here. A vertical load causes excess pore pressure, and a shear load causes excess pore pressure. So we can get excess pore pressures both ways, and what we do for this direct shear test for clay and silt, we have two phases. The first phase is the consolidate. We have to consolidate it. In other words, if I go back to here, if I apply this load here, and this is soil is clay or silt, well, what happens? It consolidates. It consolidates. It creates excess pore pressure. We have to let that excess pore pressure dissipate. We let it. It took 24 hours for it to dissipate last semester in our consolidation test. So we may have to do that during our consolidation phase. We may have to, we apply that vertical load and we let it, may take 24 hours. So this test is not necessarily, this is not a quick test for clay and silt, for a drained loading. So we're talking about clay drained. So we apply the P, vertical load, then let time pass until it's dissipated. Could be 24 hours. So that's the consolidation phase. We have not applied any shear yet. Then the second phase, the shearing phase, is phase 2, where we increase F until failure. Now, if we were going to increase F quickly, that creates an undrained shear test. If we increase F slowly, that's the drained shear test. So let's contrast the two. If I have an undrained test and we measure the excess pore pressure, so we don't always do it because it's a little bit tricky and it costs money, but I mean there's nothing, it's done all the time. But let's look at this plot here. So we've seen this part of the plot where we increase the F until we get failure. We've looked at that. Now what we're doing, so the x-axis is delta. Now we plot this directly underneath. We have everything line up here. So in other words, this delta applies to this axis, it applies to that axis, and notice we line them up on the to the left here. So that what happens is, the way that I plot this is that we put on a little bit of F, and then for that amount of delta, we also get some U excess, so we plot that as well. And notice that this graph is such that a positive number is downward. So in other words, increasing is downward. So it's it's the way everybody plots it. So just be aware that the plot is sort of upside down on the y-axis. Then so we do that. Oops. So for that value of F, we measure that value of U excess. Then we increase F to there, and we measure that value of U excess. Then we increase F to there, measure that value of U excess. Increase F to there, we get that value. There, we get that value. And we end up with two curves. We get a curve at the top, we get a curve down below. So by doing this, we get both F and U excess versus our delta. And that is an undrained test. So in other words, we're doing this quickly so that we deliberately do this to get that U excess. That is, by definition, an undrained test. If we do a drained test, now suppose we do a drain test with the excess pore pressure measured, well, what happens, okay? So we do this very slowly, in a sense. Like we can increase the F to that point, and we get a little bit of U excess, say. Now, we don't really run it this way, but then we can pause and wait. And then the excess pore pressure goes back to 0. Then we increase the F again. We get another little increase, and we pause and wait till it goes back to 0. Increase it again, and then get a little bit and pause and wait. Increase it again, we get a little bit, pause and wait. In other words, we make sure, we don't really do it, we just run it really slowly, but conceptually you can envision that if I put on just a little bit of F, if I put on a little bit of shear, I'm going to generate some U excess in a sense, and we just want to make sure that that U excess dissipates so that when I look at the plot, there's my curve for my F, but my U is just straight across, basically. It's 0. So we want U excess to be approximately 0 for the entire shearing phase, and that is a drained test. And we're measuring our U excess. But if we've done it properly, our U excess on a drain test, by definition, if the excess pore pressure is not 0, it's not a drain test. So this is just illustrating that that's how the U excess becomes 0. And of course, we have to do this on a saturated clay. So there's water there. Otherwise, We're not going to, in this class, like I said, we're taking our clays as being saturated. Because why? Well, it's a whole nother subject if we have partially saturated dry clays, dryish clays sitting at the surface. As we go deeper in the ground, what happens? The soil becomes saturated, and so we're using saturated clay for this class. In our previous class, we did that. So let's look at this example down here. Let's say that we do 2 direct shear tests, and remember the abbreviation for direct shear is DS. These tests are run on the same clay, 2 different tests. We're going to plot them on the same plot. It's going to be drained shear, so that means if I'm not going to even show the U-excess, it's going to be 0. And so I am just going to show the F and the delta. So we've got our F and our delta. And this is we applied the 10 kilonewtons. We got 8 kilonewtons for F max. We applied 20 kilonewtons, and we got 11 kilonewtons for our F max. So, and again, just to keep the math simple, we'll use 1 square meter. And the loading is slow, so that we get our U-excess as being 0. And what we want to do is we want to find C prime and phi prime. How do we do that? Well, we've got a little table here. We have test 1 and 2. We have our 2 P's, which are 10 and 20. The area is the same for both of them. And I get sigma prime FF, which is what? It's 10 over 1, 10. 20 over 1, 20. So that's our sigma prime FF. Our FFF is 8 and 11, so we get that from our test result. And then we get our tau FF, which is F over A. So we get 8 and 11. Well, that means what? Now I'm going to plot 2 points. I'm going to plot 10, 8, and 20, 11. So 2 points. 10, 8 is there. 20, 11 is there. And now I'm going to draw a line connecting those 2 points, and that is my failure envelope right there. So to get this problem to work, I need to figure out the equation for that line, or not to problem to work. To answer my questions, I write the equation of this line. Whoops. I write the equation of that line right there. Well, I use these 2 points. So you can all write the equation of the line given the coordinates of 2 points, but I'll review it here. We know that our slope is delta y over delta x, so I take the delta y, 11 minus 8. I take the delta x, 20 minus 10. That gives me my slope of 0.3. And I can get my phi prime. Now remember, the phi prime is simply that angle there. So the angle, again, is the arctangent of the slope. So I get the arctangent of 0.3, I get 16.7. To get the intercept, I'm going to use y is equal to mx plus b. And notice y is what? Tau. X is sigma prime. So this becomes tau is equal to m sigma prime plus b. Well, we've already got the m. We figured that out. The m is 0.3. So I'm going to put that in there. And then I'm going to take 1 point. I could take 10.8. I could take 20.11. For this one, I'm taking 10.8. So I put in my 10 here. I put my 8 there. I've got my m is 0.3. The only unknown is b. I'm going to solve that expression for b. And I get b is equal to 5 kilopascals. That's my intercept, and by definition, my intercept is, we call it C prime, and so my C prime is the same as B, which is 5 kilopascals. So I've determined both phi prime and C prime. Those are the parameters for my my drain strength for my clay, C prime and phi prime. All right, so this is one for you to work. There, find my C prime and phi prime given this stress strain curve or F delta curve, and note that the cross sectional area, pretty simple, 0.1 square feet. So fill out this table just as we did before, and then draw in your line and solve write your equation y equals mx plus b and find your C prime and phi prime. Okay, so pause the video now. All right, I assume that you've done that. What do we have? It's pretty straightforward. So we have our p's are 100, 300. So we have 100, 300. A is 0.1. Our sigma prime FF is what? It's 100 over 0.1, 300 over 0.1. So 1,000 and 3,000. Our FFF are what? Well, it's 30 and 60. 30 and 60. And our tau FF is FFF over A. So 30 over 0.1. 300. 60 over 0.1. 600. So I now have determined both the sigma prime FF and my tau FF. Remember, FF stands for at failure on the failure plane. So I'm now going to plot these points: 1,300, 3,600, 1,300, 3,600. I'm going to draw a line between them. So again, I want to get the equation of that line. And so delta y over delta x. So delta y, 600 minus 300 over delta x, 3,000 minus 1,000. That gives me an m of 0.15. My friction angle is the arctangent of the slope, which is arctangent of 0.15. I get 8.53 degrees. Then I want to use my y is equal to mx plus b. And the y is tau. The x is sigma prime. I can pick either point. I could pick this point. I could pick this point. Doesn't matter which one I put in, if you remember. I'm going to choose this one. So for my sigma prime, I put in 1,000. For my tau, I put in 300. Don't flip those. That's one mistake people make, is they flip their y and x. Y or x and y, flip x and y to be y and x or something like that, but don't do that. And then I solve this expression for C prime or the B or whatever, it's the same thing, and I get C prime is 150 PSF. So that's my intercept, 150 PSF. My friction angle is 8.53 degrees. Okay. Now, this is the summary for drained strength. What do I know? If I have sand and gravel, this is what you need to know. So I'm reiterating this. You should know this by now. For sand and gravel, what happens? The failure envelope is a line through the origin. And that line, then, since it's through the origin, is defined simply by phi prime, the angle. For silt and clay, it's different. It's a line that doesn't go through the origin. So we have to have both C prime and phi prime to define that failure envelope. So you can say the drain strength parameters are C prime and phi prime. For sand and gravel, C prime equals 0. So that's one way to write it. But for sand and gravel, everybody just knows that C prime is 0, and all you need is a phi prime. But for silt and clay, drain strength parameters, you need to know that term. What are the drain strength parameters? Well, they're C prime and phi prime. And so what does that mean? For sand and gravel, drained. Silt and clay, drained. Here's our line. That means what? If I have stresses in this region, there's no failure. If I have stresses in the field, I'm talking about stresses in the field, in this region up here, well, then I get failure. So I can look at those stresses in the field and figure out whether I'm going to get failure or not. Same thing down here. I have no failure below, I have failure above. So we look at the stresses in the field. If they're down here, there's no failure. If the stresses in the field are up there, well, we have failure. We don't want that, generally. So that is our summary of the drained strength of sand and gravel and silt and clay. So this summarizes drained, and then the next video we'll talk about undrained strength of silt and clay. Remember, in sand and gravel we're always going to have drained, except for instance like earthquake loading, which we are not covering in this class. So, okay, I'm going to stop there.